Okay, folks, still in section 2.3. This will probably be the last lecture video from this section, and it's on another theorem called the Squeeze Theorem. Okay, let me just double check. I believe the proof might be in the book. If you take Math 130, I might have mentioned that at some point in our class. Math 130 is the upper division version of, it's called analysis, but it's really calculus, rigorous calculus where you prove things. In that class, you actually prove this theorem, which is kind of cool. So any math majors or anyone who wants to become a math minor, you'll prove this. The picture kind of shows is intuitive enough, I think, to justify this theorem. So it's kind of fun. I tried to color code it. So let me just sort of read through it, sort of try to explain it, and then we'll do sort of a specific example, look at a couple functions. Again, I'll try to use these colors to kind of demonstrate it. Okay. So first of all, let's suppose we have three different functions, though. Three different functions. We've got f, we've got g, and we've got h. Okay, so we've got three different functions. If this is true, and so the way I read this is f of the function values of f are less than or equal to the function values of g, and then simultaneously the function values of g are less than or equal to the function values of h. What does that mean? That means that essentially the graph of f is underneath or below the graph of g, right? Because or maybe they touch at certain points. So the equal means they might touch, but other than that, the graph of f must be below g, and same idea, the graph of h must be above this g function. So g is kind of in the middle or kind of squeezed between these two other functions, which is why we call this the squeeze theorem. Okay. So suppose we say that's true, and this is an important caveat regarding limits in general, is suppose this is true when x is near a. And what do I mean by near? I put that in quotes. In other words, if we're going to take the limit as x approaches a, remember, we don't necessarily need to know what's happening by letting x exactly equal a. Sometimes we can, using direct substitution, right? That was in the previous videos, but sometimes we can't. But we don't need to know exactly what's happening there to evaluate a limit. We just have to get closer and closer and closer and see if we can observe a trend, right? Observe where the function values are going. So, in other words, we want this inequality to be true when x is near a, so we can take the limit as x approaches a. Here, except possibly at a. What does that mean? It means at a, let's say this function is not defined when x equals a. That's a common possibility for this type of thing. So g of a might not exist. However, the limit as x approaches a of this g function could still exist, right? We've seen plenty of examples of that. So that's the idea right there, all right? And none of this is really relying on function values at all. So it could be true that none of these functions exist at that value when x equals a, at that particular x value. It could be that none of them exist, but so long as these two limits exist for h and f, then we're going to draw a conclusion about the limit for g. Okay, so the top line essentially says we've got this function g sandwiched in between these two functions f and h. Okay, what this next line says is, let's say, suppose the limit as x approaches a of f of x, right? When we say it equals L, we're really saying two things right there. We're saying, first of all, the limit exists. Otherwise, we couldn't say what it's equal to. So we're claiming this limit for f exists as x gets close to a. And then whatever value it equals, we're just calling L. Right, so L is the limit. And what this equal sign tells us is that the limit as x approaches a of the h function also exists and equals the same limit. Right, so you could write this without the L and just claim that this limit equals this limit. That's really what we're saying here, is that the limit of the two sort of outside functions, the lower function and the upper function, those limits are the same. And the only reason to include the L is if that limit exists, let me just call it something, right? Let me give it a shorthand name because I want to mention it later. Okay, so the theorem says you've got this function g sandwiched between two functions. As x gets close to a particular value, which we're calling a, the two functions are getting close to a particular limit value, which we're calling L. And then the conclusion is then the limit of this middle function, the limit of g, as x approaches a, must also be L. Okay. So there, I'll leave that up there. I guess you could pause the video. In class, usually I would say I'll leave that up there so you guys can finish copying it down, but that's the nice thing about videos. You guys could pause that. So let me erase the theorem here, and I'll give a specific function f and a specific function h that we can sort of evaluate, and then I'll use sort of an arbitrary graph of the function g, but I won't exactly say what it is. Okay, so let's get rid of all this. And so the functions I want to use for my lower function, I want to keep things kind of simple. So I'm going to say f of x is equal to negative x squared. All right, and what color was my previous thing? I guess it doesn't really matter. G of x, h of x, the upper function, let's just use positive x squared. Okay, so we've got that. And let me write something about about g, the function in between here. I'm going to write this. Suppose g of 0 does not exist. Okay, so I'm creating a function g, and I'm not going to put a rule for this. I'm not going to have an algebraic rule for this. I'm just going to describe it in words. Suppose g is some function where the g of 0 does not exist, but for all x not equal to 0, so in other words, for every other x value, and I'll just write the sandwich, and I'll just do it in with the inequality. I'll just do it all in one color. But let's suppose the if statement from earlier, that f of x is less than or equal to g of x is less than or equal to h of x. Okay, so we're g. I'm claiming you could argue the domain of g here, if I wanted to do interval notation, is negative infinity to 0, round bracket because I'm not including 0, union 0 to infinity. Okay, and that's explained in words up here. G of 0 doesn't exist, so I have to remove it here. For all other x values, it does exist. Okay, but I'm not telling you what it looks like, what it does. But we know that it's sandwiched between f and h. Okay, so let's show what g might look like and see. Oh, and the limit I want to find. So let's say find limit as x approaches 0 of the g function. Okay, we know g of 0 doesn't exist, so the function value doesn't exist, but we've seen examples the limit might exist, and in this case the limit will exist. So let me just do a real rough sketch of what this scenario looks like here. Okay, so my upper function, my upper boundary, x squared, is just an upward facing parabola. All right, so looks something like that, and I kind of missed it right there, but let me see if that's visible on the. That looks pretty good, right? So that graph should pass through the origin right there, so that looks fine. So from that video perspective, looks exactly like what I want it to look like. So this thing right there, I don't need to label it. You guys can say x squared is blue, and negative x squared is the same parabola just reflected across our x-axis, right? So it lives down here, and so I've got the upside down image of that parabola right there. Okay, I see the rating doesn't show up too great on your video, but I think that looks pretty good. So I've got this lower boundary here, my f function, and I've got this upper boundary here, h. And then I know that g is somewhere sandwiched in between these two functions, right? G does not exist at the at 0. So g of 0 doesn't exist. What do you guys think the limit of g as x approaches 0 of this function g is equal to, right? So in other words, g might be like this, right? G maybe is this purple graph up here, right? So maybe it lives way up here. Right? Maybe it looks like kind of like a little sine wave or some kind of wave that's coming up here. But at some point, maybe it touches the blue graph, right? So it could be equal to my h function. It could touch that blue graph, but it can't become above it, right? So I can't do that all of a sudden because now the g function is above h, and that's never true, right? G is always below my blue function, which is h right there. So that can't happen. So it can't cross. So it might touch, but that means after it touches, it would have to kind of turn and be below this blue graph, right? Maybe it goes down and touches the red graph. Maybe that's a possibility, right? But same idea, it can't pass below the red graph right now because then that violates this condition right here, right? We know that the red graph f is always below the g graph, so it can't cross. So if it touches the red graph, it has to kind of turn and stay within there, right? So look at these things. They're kind of squashing down to that one spot. What do you think the limit as x approaches as x approaches 0, what do we think this purple function has to go to, right? Could the limit be way up? I know g of 0 doesn't exist, but could the limit be that, right? Could the functions go there? No, how would they go there? The only way they could go there is if they were getting close to there as x gets close to 0, right? So as x moves to 0 from the left, if the limit was up there, the function values would have to be trending towards that spot. But they can't because they can't go above the blue line or the blue curve. Right, so it can't be up there, and similarly, it can't be beneath the red curve. So it makes sense that it kind of has to get squashed right there, right? So I'll put a little open dot, and then maybe it comes out on the other side, and who knows what it does, right? But at that spot, if you're thinking that looks like the function wants to sort of pass through the origin, it really has nowhere else to go. It's getting tapered down, it's squeezing through there. I would claim that is correct, right? Just based on the graph. So that's the kind of idea of squeezing the function down. Let's prove that analytically, though. Let's prove that by taking the left-hand limit and the right-hand limit. No, I'm sorry. By using the squeeze theorem. In other words, when I said left hand and right hand, think about what the theorem said before I erased it. We're looking at this limit. If these two limits exist as x approaches 0, and they're the same quantity, the same value, then this limit exists and has to be that same value. So if I said what's the limit as x approaches 0 for h of x, right? That's really just, I know I have sunlight on my board, so that's really just the limit as x approaches 0 of x squared, right? And at this point, I can look at the left and right hand side. I don't really have to concern myself with that, right? Let's use one of the limit properties we did earlier, direct substitution, basically. Plug 0 in, 0 squared is 0, okay? So the upper boundary, that's going to 0. That limit is 0. And I think you could argue the same thing, right? If you took the limit for the red function of negative x squared, the limit as x approaches 0 of negative x squared my f function is just negative 0 squared, which is still 0, okay? So we're meeting all the conditions, all these sort of if statements, the hypotheses of the squeeze theorem. The squeeze theorem says that if this inequality holds up, so essentially if you've got a function sandwiched between two other functions, and then as x approaches some particular value, those two functions are approaching the same value, right? Those two limits exist, they're both approaching 0, then the function that's squeezed in between has nowhere else to go. The limit has to agree with that. It has to also go to 0. Okay? Kind of a cool theorem. Sometimes I've seen it called the sandwich theorem, so you could see that too, kind of sandwiched between those two functions. Cool stuff.